In this video, we are going to discuss how Bayesian inference can be used to update beliefs. The situation will be as follows. So we always start with a model. This model reflects our statistical knowledge, in this case about a face contour line. You can see a face facing to the right side. The dark blue line indicates our most expected instance, while the blue region indicates a region of variability where we statistically expect faces to lie. This can be a standard shape model, for example. Now we make three observations. So we know about the location of three of the points, one at the eye, one at the nose and one at the mouth, and want to integrate this additional knowledge stemming from this observation. These are concrete points and they can be possibly uncertain. Now, given the model and the observation, we want to derive a conditional model which is always consistent with our observation but still depicts our phase distribution, which are all of faces which are all consistent with the observations themselves. And you can see we still have variability while we match all the points. In this setup of Bayesian inference, the model would be called a prior belief, while the observation adds more knowledge to our prior belief and updates into the posterior belief is exactly what Bayesian inference formally describes. This formal description is based on the laws of probability calculus to achieve consistency. Our models will be mainly joint distribution models, so as you've learned in the shape modeling course. So given a distribution of 2 points, I would like to quickly repeat two basic operations we can take here. So the first one is a marginal model. Here we are interested just in the distribution of certain points only, for example just x1 in this case. It can be easily obtained by summing over the other points which we are not interested in. The second basic operation would be the operation of conditional probability, and here we would be interested in the distribution of points conditioned on known values of the other points. So in the same setup we would be interested in the distribution of x1 conditioned on the exact value of x2. And here it is slightly more complicated to calculate. We have to evaluate the joint density and divide by the evaluated marginal density of our observation. However, if we work in a Gaussian setup, both of these operations are straightforward and can be solved in closed form. Let's start our discussion of Bayesian inference with certain observation. So given our initial model, our prior belief, we now make three observations, these three exact points. So the values of these points are exactly known. We are interested in the distribution of the blue face points, here indicated as a capital X, after observing these three orange points. So formally we would write it down like this. We have a conditional distribution of all our blue points conditioned on the three observed values. This can be solved using a conditional probability operation as introduced before. So just applying this definition, we would then have the joint distribution divided by the evaluated marginal of the observations. So it is quite straightforward to find our posterior belief, which would just be this conditional probability. Now, in order to make it more general and widely applicable, we reformulate this a little bit. So in a step towards Bayesian inference, we would update the belief about phase points, the blue capital X, by observing these orange points. So we would turn our prior belief of phase points into a posterior belief of phase points. In order to make it more accessible, we will now factorize the joint distribution into two factors. So given our joint distribution of all the points, we can factorize into these two factors where we have split it into a conditional probability and such a marginal probability. This is just a basic operation of probability calculus. Now, using this factorization, we can rewrite the conditional distribution used above. So given our posterior belief, which we calculated like this so far, so joint divided by the evaluated marginal, we can now replace the joint by our factorization. And if you don't recognize this formula here, let me replace into a more general setting. So we would now call all the blue variables query variables and the observed variables, the orange ones, evidence variables, to get rid of all the x's we have. So if I rewrite it, we would here recognize Bayes' rule. So far we have only treated a certain observation. What should we change now if observation becomes uncertain? So we still observe 3 points, however the points are allowed to wiggle a little bit. We are not perfectly sure about the exact location of all these 3 points. So we call this uncertainty. We can solve this problem still using conditional probability. However, the joint distribution we need for this will be more complex, since it needs to model also how observations are distributed. We will apply the same factorization here, so our joint distribution is factorized into these two factors, and now it is at the time we speak about the names of these factors. So we have first the likelihood factor, which is the probability of the evidence given the query variables, and we have the prior probability, which is just the distribution of the query variables. So given this factorization of the joint distribution into likelihood and prior, we have now a way more flexible way of treating a joint distribution. And these two factors actually make sense also from an interpretation point of view. So we first have the prior factor, which is the distribution of our core model without any observation. So it is our prior belief, our prior knowledge. On the other hand, the likelihood describes how observations are actually distributed, how we expect to observe values in these models, and they characterize our uncertainty of observation, for example. And these two factors really separate these two parts into the prior knowledge and the observation knowledge. Now let me give you an example where we have Gaussian distributed points. So let's start with the prior. In a Gaussian setup, this would just be a Gaussian distribution of the actual point location here of this blue point. The likelihood, on the other hand, would be an observation model. So what do we expect from the observations we take? How certain are we about these observations? So given an actual point in blue, we expect to measure somewhere in the red region. However, since we are in an applied setup where we always have an actual observation, we always evaluate this likelihood at a certain point. Bayesian inference is the formal rule to update our beliefs. And we do so using just Bayes' rule, as introduced above. This also works for uncertain observations, provided that I use the proper likelihood here. The factorization also introduced the prior, which is our knowledge about the query variables without making any observation, and both of them together yield the posterior when we actually normalize it with the marginal likelihood. So with each observation we update our beliefs and change our knowledge. So we would, by applying Bayesian inference, update our prior knowledge about Q into a posterior knowledge about Q given our observations E. We can do this again and additionally introduce an observation f and do it even again to go to an observation g. In this step-by-step appliance, Bayesian inference kind of evolves our beliefs with growing knowledge. So our knowledge would grow from observing E to F and G at the end, and Bayesian inference is there to integrate all those additional facts. In some situations we might not be interested in all parts of our model. So given our 3-point observation setup, we might just be interested in the distribution of the points of the nose. So in this case, our models actually contain irrelevant or hidden variables. So in our example, this would be the noise, the points around the chin, when we want to actually talk about the nose distribution. The Bayesian way of treating these hidden variables is we just marginalize over these variables, and remember, this is the second operation introduced above, and it is just a summation over these variables we are not interested in. So given our posterior including both variable sets, the actual query variables and the hidden variables, we would just sum away the hidden variables. Bayesian inference is a very general method. So in a typical application, we do not, or very often we do not directly observe a specific part of the model itself. So a formal part in our case would be the point itself. But in a practical application, we very often observe derived data such as a face rendering or landmark locations after a coordinate transform. However, we could still couple these more general observations to our core model via this likelihood factorization. And it all works as introduced above, but just uses a little bit more complex likelihood. So in this general case where Bayesian inference is mostly applied, we would talk of the evidence data we had above as simply data. This is the data we observe, and it doesn't have to be a directly modeled variable, but can be integrated using a likelihood. On the other hand, we are usually interested in parameters of our model, which would be our query variables. So written with theta and d, our Bayes rule posterior becomes this expression where we still have the posterior is the product of the likelihood and the prior, and we normalize with the marginal likelihood of our observation. This marginal likelihood is very often intractable to compute, and a lot of methods exist which just use a kind of a proportionality here, such that we only consider the product of likelihood and prior.